Hey, how's everyone doing today? Pretty good. Good to hear. Good to hear. Kind of a miserable day outside today, but alrighty. Okay. So let's finish up looking at triple integrals. All right. Okay. So we saw yesterday how to do triple integrals. We're integrating a function of 3 variables, x, y, and z, over some solid region in space in R3. So we saw yesterday how to integrate over a box. So if B, the box B, say x goes from A to B, y goes from C to D, z goes from P to Q. So the first coordinate is x, the second is y, the third is z. The way we integrate, do a triple integral of f of x, y, z with respect to volume over the box B is we created an iterated integral. And by Fubini's theorem, you can integrate in any order you like. You could do z then y then x, or z then x then y, or x and y then z, x, z, y, y, x, z, y, z, x. Any of those 6 orders works. So you could do, say, z first. So z goes from P to Q. Then say y, whoops. Y goes from C to D. And then say x. X goes from A to B. Any order is fine. That's Fubini's theorem. They're all equal. So if x, y, and z are all bounded by numbers, you're integrating over a box. You can integrate in any order you like, and it works just like double integrals, except now you have one more integral, one more iterated integral you need to perform. We also saw that we can integrate over more general regions. So similarly to double integrals, we have simple regions, different types of simple regions, simple solid regions in R3 that we can integrate over. And we looked at z-simple regions. Let me give myself more room, that's fine. So z-simple region, similar to vertically simple and horizontally simple in R2, but now we have 3 dimensions, right? So we can have a top and a bottom surface. So if we look in the z direction, we're bounded above z by functions of x and y. So z is equal to some function of x and y. That's a surface, a top surface, and a bottom surface. So our top surface is going to be z is equal to, say, g2 of xy. And our bottom surface is going to be z is equal to g1 of xy. So z is going to be the guy bounded by functions. So say we have a top surface and a bottom surface. Let me draw this a little better. So there's our top surface, there's our bottom surface, and then x and y, when we project this down, so if you think of taking this solid region and smashing it down to the xy plane, projecting it down there, the shadow of that guy is going to be where x and y live. So this is our solid region W. We have a top and a bottom surface, and we say x and y lie in D. So if you think of this region D, that in the XY plane, if you extend this in the positive, negative z directions, that kind of gives you the sides of your z simple region. This is a really kind of a terrible illustration here, but top surface, bottom surface. And then for x and y, you project this guy down to the xy plane, and then that is where we say x and y live. So we say z lies between g1 of xy on the bottom, g2 of xy on top, and then we say x and y lie in D. So it's the set of points x, y, z satisfying these. So this is a z simple region, top surface, bottom surface, and the sides are given by where x and y live. So the way we integrate a function of 3 variables over a z simple region is, well, z is the guy bounded by functions of x and y. So z is bounded by functions of the other 2 variables. So we need to integrate with respect to z first. So z is bounded by g1 of xy below and g2 of xy above. And so that's going to be our first iterated integral. Integrate with respect to z. And then you're left with a function of x and y. Think of smashing this down to the xy plane. And then we integrate over the region D where x and y live. Now this is just a double integral. And we know how to perform those. And I leave this specifically ambiguous here. I say just integrate over D, because depending on the shape of D, you can integrate with respect to y first or with respect to x first, or do some other stuff, as we'll see later when we cover other coordinate systems. But yeah. So z simple, top and bottom surface, Z is bounded by functions of x and y, so we integrate with respect to z first. And then after you do that, you're left with a function of x and y, and you integrate that function over the region D where x and y live. And how that works depends on what D is. Yeah, so when you integrate with respect to z, like with double integrals, you integrate out z, right? So z gets replaced with something in like a number or stuff involving x and y. So you're only left with a function of x and y. Right, so then that gets integrated over the region D where x and y live. Yeah. Okay. So we did an example yesterday, which I won't go over again, but let's do a similar example to that. So we're going to have the same top surface and bottom surface, except now the region D is going to be different, and we'll see how that works. So I'm mostly just going to set up the integral, do like one step of that, and then go for it, because we know how to evaluate the integrals. That's not the hard part. It's setting up that's the important thing. So we're going to evaluate the integral over the region W of z, the function z with respect to volume. So here W is bounded above by z equals, whoops, 3x plus 5y below by z equals x plus y. And this region is going to lie above the triangular region in the xy plane with vertices 0, 0, 0, 1, and 1, 0. Why are you like this? So we did this example, except the region D was different yesterday. Yesterday, the region D, it lied above a rectangular region where it was the rectangle. So we're just gonna power through this one really quickly because we did a chunk of this work already. Okay. So this is a z-simple region. We have a top surface and a bottom surface. So we're told our top surface is 3x plus 5y, z equals 3x plus 5y, and our bottom is z equals x plus y. So we have bounds for z already. We're also told that this lies above the region, the triangular region in the xy plane with vertices 0, 0, 1, 0, and 0, 1. So let's sketch that real quick. That's going to be our D. So that's our D. And we'll come back to that in a sec. Okay. So it's z simple. So z is bounded by functions of x and y, so we need to integrate with respect to that first. So z goes from x plus y to 3x plus 5y. We're integrating z. So we integrate with respect to z first. And then we have a function of x and y, and we integrate that over the region D in the xy plane. And we'll set that second integral up in a second. So we saw yesterday, when we do this inner integral, we get 1/2 z squared from x plus y to 3x plus 5y. When we simplify that, we get 4x squared plus 14xy plus 12y squared. Whoops. Goodness, hang on. There we go, TA. So this is the same as what happened yesterday, but now the region D is different. And so when we evaluate this double integral here, we're going to set that up differently because now D is now not a rectangular region, it's a triangular region. So how do we want to do this? Okay, so is this vertically simple? Horizontally simple? Both? Neither. The region D. We now have a double integral. So it's both. So you can do both, but usually it's easier to think of things as vertically simple because we like to write curves as y equals something, y equals something. And in fact, we're given, well, no, we're not given this yet. We're not given this yet. So let's go ahead and do this as vertically simple. So there's a top and bottom. So I'm sorry, go ahead. Yeah, go ahead.
I just had a quick question. So how did you get from z dz to the 4x squared plus, and then like the rest of that?
Oh, we did that yesterday. So I just wanted to save some time, but so we're integrating with respect to z. So z becomes 1/2 z squared. And then when you plug in 3x plus 5y and x plus y, so you get 1/2 times quantity 3x plus 5y squared minus x plus y squared. And then you FOIL those out and then bring your terms together, and that's what you get.
Okay, gotcha. Thank you.
So that's like not the important part. It's like the setting it up. Everyone knows how to evaluate integrals, but yeah. But yeah, we did this at the end of class last time. Okay, so for D, what is our bottom curve? Y equals what? Y equals 0 is our bottom curve. And our top curve is y equals what? One minus x. So if we treat it as vertically simple, we integrate with respect to y first because y is bounded by functions. So y goes from 0 to 1 minus x. X goes from, hang on, let me plug this in. So 4x squared plus 14xy plus 12y squared. Integrate with respect to y first. And x goes from what to what? So y is bounded by functions, x is bounded by numbers. So x goes from 0 to 1. And then that's another evaluation, which I'm not going to do. But if you wanted to check what you should get there, it's 23 over 12. But the important bit is noticing it's a z-simple region. We have a top and bottom curve. And then we're told explicitly where x and y live. And that's going to be your region D. So then often it helps to draw a picture of D. See if it's vertically simple, horizontally simple, etc. We saw it was vertically simple, so on and so forth. Okay, any questions about?
Where did the bound of 1 minus x come from?
So we have this triangular region with the vertices 0, 0, 1, 0, 0, 1. And so we know that the bottom curve is this guy y equals 0, the y-axis. Sorry, x-axis, my goodness. And the top curve is this line here. And so that's just a line with slope -1 and y-intercept 1. So that's where we get the 1 minus x. Does that make sense?
Yes, thank you.
Okay. All right. So let's look at a slightly more complicated thing. Not too much more complicated, but. So often we're not given explicitly what D is, where X and Y live. Sometimes we have to figure that out for ourselves. So specifically, this happens a lot when you have a region which is enclosed by intersecting surfaces. Okay. So let's evaluate the integral over the region W of the function x with respect to volume. So here W is going to be the solid region bounded above by z equals 4 minus x squared minus y squared, and below by z equals x squared plus 3y squared. And let's say this lies in the first octant. So remember, the first octant is just the part of R3 where x, y, and z are all positive. That's like the first quadrant in the plane, except it's where x, y, and z are all positive. Okay, so really, here now we just have basically two surfaces that are intersecting. And we're not told exactly where x and y live. We just know there's a top surface and a bottom surface, so the bounds for z are easy. But now we got to figure out where x, y, and z live. So if possible, just do a really rough sketch to try to get an idea of what's going on. Sometimes this is a lot more difficult than others, but this one is not too bad to do. So let's forget about that first octant part. We'll come back to that later. But so we're told we're bounded above by z's 4 minus x squared minus y squared. That's an elliptic paraboloid opening downwards, and the z-intercept is going to be 4. And then below by z equals x squared plus 3y squared, that's going to be an elliptic paraboloid opening upwards. And the z-intercept is going to be 0. And it's not going to be exactly circular. It's going to be a little elliptic there, but that part's not too important. So forget about the first octant part. Here's our top surface. Here's our bottom surface. And we need to figure out where x and y live. So we need to figure out D. That's the hard part of this. So for D, we basically want to look at the widest part of the shadow of W on the XY plane. This is how you want to be thinking about this. So here's how I think about this. So this is our region W, our solid region. What we're going to do is we want to know where X and Y live. So we're going to take W and we're going to sort of flatten it down onto the XY plane, or look at the shadow of this guy in the XY plane. So we want to figure out what the outer bound of this shadow is. And so look for like the widest part of the shadow on here. So if we project this down to the XY plane, if we look at the shadow of this guy, the outer curve of the shadow, the outer part of it, that's the widest, that's going to come from the widest part of W. Where does the widest part happen? How would you describe that? So you're on the right track. You probably mean the same thing. How would you describe that in terms of the two surfaces? The top surface and the bottom surface. It's right, it's the intersection. So here, the widest part of W, this is really hard to read, is the intersection of the surfaces. So the widest part is going to be the intersection of the top and bottom surfaces. So basically, we're going to look at that intersection projected down to the XY plane and then go from there. Does everyone see that? That's the easiest way I find to do this sort of thing. Make a really rough sketch. Think about where the widest part is, and then project that guy down to the XY plane. Okay, so let's look at the intersection of the top surface and the bottom surface. So the intersection, well, we have z equals something, z equals something. The intersection is going to be the set of points they have in common. So all the z coordinates of those points are going to be the same. Well, we have z equals something, z equals something. So set those guys equal to each other. 4 minus x squared minus y squared equals x squared plus 3y squared. Or in other words, we have bringing x squared and y squared over. 2x squared plus 4y squared equals 4. Or to sketch this a little more easily, let's divide by 4 to get it in sort of the standard form of an ellipse. So we get x squared over 2 plus y squared equals 1. So when we project this down to the xy plane, if we forget about z and sketch this guy in the xy plane, this is going to be an ellipse. What is the x radius of this ellipse? So how far along in the x direction does the ellipse go? Careful. So remember, remember we had, when we were drawing traces, we looked at x squared over a squared plus y squared over b squared equals 1. And here a is the x radius, and b is going to be the y radius. So then our a squared in this case would be 2. So then what is our a? What's our x radius? So you're going in the opposite direction now. 2 is our x squared, our radius squared. So it's actually going to be root 2. Yep. So it goes root 2 in the x direction. And in the y direction, the y radius is going to be 1. So this is going to be the outer bit of our region D. But that's so if we forget about the first octant thing, if we just look at the top surface and the bottom surface, project this down to the xy plane, the region inside of that guy is going to be our D. But we're told that we're just looking at the bit in the first octant where x, y, and z are positive. So when we project that down to the xy plane to see where x and y live, we don't care about z anymore. But if x and y are both positive, so it's going to be in the first quadrant. So this is our D. So it's the bit inside that ellipse, which lies in the first quadrant. Okay, so that's our D. Okay, so let's figure out the bounds for D before we set up our integral here. Okay, so is D horizontally simple, vertically simple, both? Neither. It's both. The book treats it as horizontally simple because it slightly simplifies the way the bounds look, but let's just do vertically simple. That's easy to do as also. So bottom curve is easy. That's y equals 0. How about our top curve? Well, our top curve comes from this, and it's going to be the top half of that. So then just get y by itself and take the positive branch of the square root. So this is going to be y is equal to square root 1 minus x squared over 2. So y goes from, whoops, y equals 0 to y equals 1 minus x squared over 2. And how about x? X goes from what to what? Zero to root 2, right? Careful, you're probably tempted to say 0 to 1, but it's 0 to root 2 in this case. Okay, so now let's set up our integral. I'll come back to this page in a sec when we do this, but okay. So the integral of x with respect to volume over w. So it's vertically simple. We have a top and a bottom surface. So z is bounded by functions of x and y. So we need to integrate with respect to z first. Let me give myself more room. So we said z. Right, so z, the top surface is z equals 4 minus x squared minus y squared. And the bottom is z is equal to x squared plus 3y squared. Okay, so let me give you a small bit of advice that'll help in the future when we're doing integrals, especially when we get to cylindrical and stuff. This is gonna make life a lot easier. So let's just plug in the bounds for d later. Right, so do the first integral. Get your integral over d, and then figure out your bounds for d. That's going to make life easier later. Oh, because we're told that's the question. That's the function we're integrating. Yeah. Okay. So let's just do the inner integral. So we're first integrating with respect to z. So what happens with x when we integrate with respect to z? What do we get? So everything but z is a constant. So x becomes what? Xz, right? X is just treated as a constant. And we evaluate that from z equals x squared plus 3y squared up to z equals 4 minus x squared minus y squared. So we can pull the x out. So 4 minus x squared minus y squared minus x squared plus 3y squared So we get 4 minus 2x squared minus 4y squared times x. So we get 4x, just multiply everything through, minus 2x cubed minus 4xy squared. Okay, so that's our inner integral. Let's plug this into the double outer integral here. And then we can plug in our bounds for d. So 4x minus, whoops, 2x cubed minus 4xy squared with respect to area. Oh, weird. So now we're integrating over d and the xy plane. And we figured out what d is. We figure out d is horizontal, or sorry, vertically simple, also horizontally simple if you want. And y lies between 0 and square root 1 minus x squared over 2. And x lies between 0 and root 2. So plug those guys in. So we integrate with respect to y first, because we're treating it as vertically simple. So square root 1 minus x squared. Sorry, so it's 4x minus 2x cubed minus 4xy squared. Integrate with respect to y first, because it's vertically simple. And then x goes from 0 to root 2. And once again, I'm not going to evaluate this right here, right now. But if you would like to do that, what we end up getting is 16 over 15. Okay, so a lot went into this, but for all of these guys, we saw this was a z-simple region, right? We had a top surface and a bottom surface. Often you will, Aiden, but in the interest of time, a lot of times we'll just ask you to set up the integral. And so even when we do ask you to evaluate an integral, most of the points are going to come from setting up the integral correctly, getting the right bounds. And later when we talk about change of variables, like doing that correctly.
Can you just go back to the last slide so I could like see this
Sure.
before this?
Sure. And this is where, yeah, this is where most of the points come in. So often it takes a while to evaluate integrals. So, I mean, you should always practice enough so that you're quick enough at this to do this. But if you're really running low on time, I would set up an integral, get the bounds, and move along and come back to it later if you have time. If you're worried about time, that's probably the smart move. Are we good on this slide? Okay. So we looked at z-simple regions, right? So in this case, there's a top and a bottom surface. And then x and y lying in D, some region D in the xy plane, that gives you the sides of your solid region. But of course, we have two other directions, right? So we could have a, in the y direction, a left surface and a right surface. So y is bounded on the left by y equals a function of x and z. On the right by y equals another function of x and z. And then we can project this to the xz plane to see where the other two variables x and z live. And then similarly, we can do the same thing for x. Oh, cannot spell. So a y-simple region, we're going to think of that as having left and right surfaces. So the left surface is going to be y is equal to a function of the other two variables, x and z. And the right surface is going to be another function. Y is equal to another function of x and z. And then x and z are going to lie in some region D in the xz plane. And that's going to form the sides. So we have a left surface, a right surface. Projected the xz plane, the region D, where they live is going to form the sides here. So we have a left surface, a right surface. Sorry, I mixed those up, but this is y is equal to g1 of xc. Beautiful picture, I know. We have a left boundary and a right boundary, and then the sides we project to the xc plane. And the region D in the xc plane where those live tells us what the sides are. And then we also have x simple. I'll show an example. I'll share the book for the x simple. Not even gonna write it down. Not even gonna write it down. Let me just share this. And for x simple, now we have in the x direction, we have a front surface here where x is smaller, and a back surface here where x is larger. So the front surface, x simple, x is going to be written, the bounds for x are going to be functions of y and z. So this is x is some function of y and z. Here this is x is some other function of y and z. Sorry, I got those mixed up. Here, this is where x is smaller, right here, and this is where x is larger. And then for the sides, we project this to the yz plane, and that region D, where they live, that's where we say y and z live. So top and bottom surface, z is bounded by functions of x and y, project onto the xy plane. That region D is where x and y live. Y is simple, y is bounded by functions of the other two variables, project to the xc plane, see where x and z live. And then x simple, x is bounded by functions of the other two variables, y and z, project to the yz plane, to see where y and z live. And the way we integrate those is the same. It's always the function, it's always the variable bounded by functions of the other two variables that is we integrate with respect to first. So if we treat it as x simple, we integrate with respect to x first. Y simple, we integrate with respect to y first. Z simple, we integrate with respect to z first. And then we're always projecting to the other two variables and then integrating over that region in that plane. And then how we do that depends on the shape of that region. Okay. So I won't do any examples of these, but any questions about anything from this chapter? Okay. If not, then that's it for today. I will see y'all tomorrow. We'll talk about polar coordinates and maybe cylindrical if we get to them. And yeah, have a good rest of your day. And I'm moving over to the office hours Zoom, and I'll see you there. And if not, see y'all tomorrow. Have a good one, guys.